Yeah.
To be valid by order 1? Or?
Yeah, so I'm assuming checking a certificate takes constant time, whether it currently holds, and computing the failure time takes constant time. Yeah. I mean, you could assume it, or maybe you pay a little more. I mean, this is how we're going to build the data structure. So whatever it costs, it will cost. But I think everything we'll talk about, and pretty much every certificate out there, is sort of a constant size thing. Some of them are bigger, but we'll get to the costs involved. Maybe we won't worry about time too much. This priority queue is going to take log n time, where n is the number of certificates in the data structure, to find when is the next failure. So if I want to do an advance, basically I'm going to do discrete event simulation. I find the next event when something changes, i.e. a certificate fails. I'm going to fix that event, fix that certificate, make the data structure correct again, then advance to the next failure, repeat. As long as there aren't too many certificates to mess me up, this advance will be fast. So, yeah. So here's how we're going to implement advance. Basically, in all kinetic data structures, we just say while t is greater than or equal to the next failure of the priority queue, we advance to that moment in time when something interesting happens. We do an event. I'll write it this way. And then we set now to t. And this event thing has to somehow fix the data structure and fix the certificates. So that is the challenge, is how do you deal with an event when one of your certificates breaks? So if you have a data structure, you want to make it kinetic, you just first write down some certificates under which it's guaranteed to be valid, and then see how to fix them as things happen. Then there's the analysis issue, which we will get to. Let's start with an example before we get to analyzing. So this becomes a little more concrete. Yeah.
So are the change operations sort of online, or do you have like the sequence of changes that you're going to do?
All of these operations are online. So at any moment, someone says advance, someone says change, or someone says query, and query is respect to now. So we have no idea which of these are coming, in what order, whatever. Don't think anyone studied the case where you know up front all the things that are going to happen. Though there are presumably applications for that. I mean, time can just be a euphemism for dimension or whatever. But a lot of the kinetic people actually really want to be tracking points and maintaining what's happening. So let's do a 1D problem. Simple one. Sort of the most basic problem, which is a predecessor problem. Insert, delete. We won't worry too much about insert and delete here. It's hard enough because the points are moving around. And predecessor and successor. So I want to know on the line, I have some points, they're moving. Now query is who's at the current time, who's to the left and who's to the right of this query. Okay. How do we maintain this? This is a problem we'll be studying a lot in this class, but the basic structure for solving predecessor, insert, delete, predecessor is binary search tree. Balanced binary search tree. Okay, so let's use a log n high AVL trees, whatever. So what do we need for certificates? I was going to use this as an example, but it's actually a little tricky to think about what the certificates are. Because the binary search tree property is x less or equal to x greater than or equal to x. That's kind of a lot of certificates. If I want to compare X to every single guy in here, compare X to every single guy in here, that would be I think, quadratic number of certificates in general. Almost everyone has a relation. I'd prefer to get away with fewer certificates, because then less certificates will fail. So, cute idea. I really only need to compare X with this one and this one. The max in the subtree and the min in the subtree. In general, if I look at the data in sorted order, it has to stay sorted order. Where it's not going to be sorted, but this is an in-order traversal. Okay, in-order traversal is something we can understand without knowing what the data is, because remember, data is constantly changing. We can't really use the keys here. But we can use the abstract shape of the tree and do an in-order traversal and say, look, as long as xi is less than or equal to xi plus 1 in the in-order traversal for all I, then this is a valid binary search tree. If an in-order traversal stays sorted, we're golden. So those are my certificates, only n of them. So that's nice. We need to check that we can compute a failure time. This is usually really easy, but we'll go through the exercise. Writing it down. So I want to know, among all times greater or equal to now, when will xi, am I doing strict here? Should probably be greater than. Yeah, so that's why I have an infimum. Okay, I take the moment, the earliest moment when xi of t is greater than xi plus 1, which is the opposite of what I want, and take the infimum of those times. And so that will be the moment of transition when they're equal, and then boom, it's going to jump over. I'm assuming these things are continuous.
That's why
So,
you take the infimum?
yeah, so I think it will be an infimum because these guys are going to cross something. I mean, I don't care about this kind of happening, but if it's going to actually go across, then there'll be the moment of transition where they're equal, and that's going to be this infimum. Okay, how do you compute that? Well, it depends what these trajectory functions are like. If it's algebraic, then this is just a polynomial thing. You can do it in bounded degree. You can do it in constant time. That's our model. Okay, so you put them into a priority queue, do this advance, and now the question is, how do you process an event? When one of these things happens, you're about to transition to xi being bigger than xi plus 1. What do you do? So that's the real heart of the data structure. Although really the heart of a kinetic data structure is the choice of certificates. If you choose certificates well, then you're going to be efficient. We haven't defined efficient yet. We will. Otherwise, not going to be so fast. So all about choosing those certificates right. The rest is kind of straightforward. So let's suppose this certificate is about to fail. And we're guaranteed by this algorithm that it fails now. We have advanced to the time when it is about to fail. We process that event. So now is the time when these two things are equal. Right after now, we will get to greater than. So here's what I do. Swap them in the binary search tree. So right now, maybe I guess in general, it's going to look something like this. We have xi plus 1, or it could be the reverse scenario, where one of these xi plus 1 is a leaf and xi is the predecessor. Right now, they're equal in value. So I'm just going to interchange them, move xi up here. So it's a little confusing, but this is xi plus 1, and this is xi. Replace those. These are really pointers to the trajectories, however they're described. Interchange them. It's still valid as a binary search tree. Actually, this binary search tree never becomes invalid because at this moment they're equal. And after now, things will continue to be okay because now this guy will be bigger than this one. That's the assumption. We just need to fix the certificates. Fixing the data structure was pretty trivial, constant time. So what certificates do we need to do? We need to add this new certificate. I'm going to call it xi prime is less or equal to xi plus 1 prime. So this is actually xi plus 1, formerly known as xi plus 1, formerly known as xi, but be really confusing. So I'm going to use the primes to be the new data structure, because this is always the kind of certificate we want. We also need to update certificates. So there used to be an xi minus 1 less or equal to xi. We want to turn that into xi minus 1 less or equal to xi prime. And we used to have an xi less or equal to xi plus 1. We want to turn that into xi prime less than or equal, oh, that one we already did. Sorry, so I want xi plus 1 to xi plus 2. And I want to do now xi plus 1 prime to xi plus 2. Okay, basically wherever the primes happen, which is xi and xi plus 1, whatever certificates they're involved in, you have to update them, meaning rip out the old one, put in the new one. And the main issue here is that you have to maintain the priority queue. So you've got to take them out of the priority queue, put them, recompute their failure times, put them back in the priority queue with that failure time. But the point is this is a constant number of updates. In general, pretty much, as long as the things you're messing with, the items you're changing, are involved in a small number of certificates each, then this will be cheap. I'm writing this explicitly, but in general, it's just update whatever certificates those points were involved in. The issue is how many things you change and how many certificates each of those things is in. In this case, changing a constant number of things, each of them is in a constant number of certificates. So it's not constant time, but constant number of calls to priority queue updates. So log n time. Yeah, question.
So, but how do you find the things that you just changed in the priority queue of the failure times?
You've got to, how do you find them in the priority queue? How do you find these xi's and xi plus 1s? Every point knows what certificates it's in, meaning it has a pointer to a list of certificates it's in. There's only 2 of them. And each certificate has a pointer into its existence in the priority queue. So then you know where it is in the priority queue and you can rip it out. Yeah. Lots of pointers and cross-linking. Yeah?
So, it's something that's pseudo-algebraic. Any certificate changes O of 1 times. But here, there's O of n squared. Even though we're only taking n certificates at a time, there's O of n squared possible certificates in each of them.
You're asking about efficiency, which we will go to now. This looks disconcerting because even though pseudo-algebraic gives us that each certificate won't change too many times, there are a quadratic number of potential certificates. They could all become relevant. And indeed, that is the case if you have these points spaced out a lot, then you have these points spaced out a little, 4 and 4. And these guys are all moving constant velocity this way, and the white guys are stationary, then what happens? Well, there's event, 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 event. Okay, you're going to get n squared events. Get like n over 2 each time you cross a wide point. I call this okay. Why? Because of efficiency. The claim is this is sort of the best you could hope to do. So in that sense, it's as good as you can hope to do. If you want to maintain predecessors, let's put it this way. If we need to know is a sort of vague thing, the sorted order of the points, then you need an event. If we're going to keep a data structure that is always accurate now, so this is sort of an assumption, then you need an event every time you have an order change. That's sort of a tautology, but it's a perspective. And what's happening here is that we have an event every time there's an order change. So sometimes, yeah, it's going to be bad. Worst case here is quadratic. You can actually prove for pseudo-algebraic, it is order n squared events. So this was really a lower bound. But it is also order n squared all the time, because if you look at any pair of guys, they're only going to change a constant number of times who's above whom for pseudo-algebraic, if there are no change events. So for efficiency, because it's really hard to analyze if points are changing their trajectories all the time, assume there's no changes. We basically just advance to infinity. How much could that possibly cost? That's how kinetic people like to analyze things. And for this problem, for maintaining sorted order at all times, the worst case answer is theta n squared. This data structure achieves theta n squared, so we consider it worst case optimal in this weird sense. Okay, this is if you really want to maintain the sorted order. Now, we didn't say we wanted to maintain the sorted order. We said we want to maintain a predecessor data structure. But it feels kind of like those are the same thing, maybe. I don't know if there's a formal sense in which this is the case. And efficiency in general is the vaguest part of kinetic. And for each problem, you have to think hard to understand what does efficient mean for this problem. But maybe don't even worry about efficiency. What does a lower bound mean? But bottom line is worst case n squared events if there are no change operations. Okay, so you can think of the running time, if you want, of jumping to infinity is order n squared in the worst case. That's how we analyze these things. There are other things we like to analyze. Efficiency is one of them. We have three others, which I sort of hinted at. There's responsiveness, which is time spent to do an event. So when a certificate is invalidated, how much time does it take to do that? There's locality, which is closely related. This is the number of, number of certificates per data object. Okay, I said over here, this is good because each item xi is only involved in a constant number of certificates. So we say the locality is constant number of certificates per object. Usually locality implies responsive. As long as you can update the data structure, you can also update the certificates in whatever. You play a log factor because you're updating a priority queue, but you can update all those events and redo all the certificates in an event, provided you're local. So locally usually implies responsive, more or less. And then what's the other one? Compact. This is about space. We just like the number of certificates to be small. So in this case, number of certificates is linear. I set up here. So we consider the data structure to be optimally compact. You need at least n. Okay, so in our case, we're getting order n here, order 1 here, order log n here. And efficiency, I guess you call constant, kind of. Efficiency is the ratio of how many events you do divided by how many events you need to do. And here it is optimal in a certain vague sense. Okay, sorry, that's a little unsatisfying, but it's unsatisfying. That's the literature. For that problem, we're going to do another problem, which is more satisfying, I would say. And kind of shows you why kinetic problems are pretty interesting. Data structures are often pretty darn simple, and the fun part is the analysis. Where it can get intricate is the analysis. So let's solve kinetic heap. Our goal is to be able to do find min. And yeah, there's also insertions and deletions, but I'm not going to think about them because they're not really that different. We're kind of like a change. Let's not worry about it. The goal is to maintain the minimum. Now, if you look at this point set, and their velocities, how many times does the minimum change? Once. Initially the min is this, eventually the min will be this. One change to the minimum. So this data structure is a bad way to maintain the minimum. Yes, it does maintain the minimum, but it's going to spend a quadratic number of events in this situation where the min only changes once. So can we get ideally you have one certificate which is like, this point is the minimum. But that's not such a good certificate because then every point is involved in it. And how do you know when it's going to be violated? I guess you could compute it in like linear time or something. It's not a good plan. We need to break down into certificates that only involve a constant number of things and maintain the minimum. And somehow I want to get below quadratic number of events in the worst case. And you can, and you do it with a heap. Okay, remember heaps? Sorry, min heap. So min heap has this property. If you have x, y, and z, then x is less or equal to y, and x is less or equal to z. This is nice because local property. These are my certificates. For every node x, I have to have this property. Okay, so I have order n certificates. That's good. I had order n certificates before, but I claim these magically are easier to maintain than those, even though they look almost the same. Kind of crazy. I don't know if I really need to write it, but how do we do an event? Okay, if x and y are about to invert in order, so currently x is less or equal to y, in a moment x will be bigger than y, I swap x and y, I update all the certificates. Okay, constant for each. It's 2 items I'm moving. Each of them is involved in a constant number of certificates, 3 now instead of 2. But constant number of certificate changes and stuff. Log n time, I update the priority queue. Question?
How is it 3?
Because x is involved, why is it 3? X is involved in the certificate with its 2 children and with its parent. Its parent has a relation as well. Yeah, so you have to be careful in counting locality, how many certificates is each object in. Okay, so we're responsive, log n time, local, constant certificates per object, compact, linear number of certificates. All these are the same. Big issue is always about efficiency. How many events is it in the worst case? How many events do I need? Okay, here, it's for kinetic heap where I want to maintain the minimum at all times is actually a very clear lower bound. The number of events, or let's say the number of changes to the min, I think this is what some people call external events. Like you can't control when the min changes. The user controls that by how they set up the trajectories. Changes to the min is at least n in the worst case. Okay, it's pretty easy to set this up. You have a point, another point moving at constant velocity to the left, it will overtake. You have another point farther away with a bigger velocity to the left, it will overtake after this one overtakes. And something like this. Got to make sure they don't all cross at the same moment. But this one will go first, and then this guy will cross over, and eventually. So that's easy to set up. Now, the min can change a linear number of times. I claim in this data structure, well, of course, the min will change at most a linear number of times. Well, it's not clear it's at most, but that's true. Well, we care about those. We're storing a way more certificates than the min. We have a linear number of certificates. I claim the total number of events in this data structure, if there are no change operations, so if we just advance to infinity, number of events is order n log n. And so we call the efficiency log n, because you're a log n factor away from this lower bound. This is the interesting part, and this requires a proof. So y is the number of events, order n log n. We're going to prove this by amortization with a somewhat tedious potential function, but it's sort of the obvious one. At a time t, I want to define my potential at time t to be how many events will happen in the future. This is the thing I want to bound. Okay, so I want to prove this is order n log n at time 0. But let's think about how it changes over time. So I'm going to rewrite this as follows. I'm going to sum over all items x, and we're thinking about the potential at time t. So I look, x is in some node, and which node it is in changes over time. But at time t, it's in some node. I look at all the descendants of that node. I look at those items, and I see which of those items will overtake x in a future time. Those are the ones that I care about. When you overtake an ancestor, that's when an event happens. Okay, I claim these two things are equal. I probably don't even need to prove that. Okay, so this is in parentheses. Don't worry about these being equal. Think of this as the potential function. Okay. Now I want to look at an event and see how this changes. I need a little bit more notation. I'm going to call this thing phi of t comma x. Okay, so phi of t is the sum over all x of this thing, which is phi of t comma x. Number of descendants of x at this time that will in the future overtake x, meaning their key will get larger than x. Okay, I can also expand phi of tx in a simple way. It's kind of trivial, but if I look at each child of x, there's two of them, call that y, and then measure how many descendants of y at time t will overtake x. So it's almost the same words, but I changed one of the x's to a y, but only one of them. So in future I write greater than t. Okay, this is a different quantity, slightly different, which I'm going to call phi of t comma x comma y. I just need to be able to talk about this, so this is mostly to introduce notation. Okay, and by descendants of y, this is including y itself. So there's y and all of its children, descendants, whatever. Which of those will overtake x? If I do add that up for both children, that is the total number of descendants of x that will overtake x. Okay, so this is equality is trivial. Mainly I wanted to introduce that. Okay, so what? Now let's look at an event, see what changes. So, a little bigger, x, y, z. Let's say we need to change it to y, x, z, because y is about to overtake x. How does the potential change? Okay, well, potential is the sum of all of these phi t x's. So, which of these phi t x's change? I claim that phi of, I'm going to call it t plus, which is the moment right after now, infinitesimally larger. I claim it does not change for most vertices. It only changes for x and y. If x and y are the guys that are switching order, this will not change for any others. Why is that? Because we're looking at number of descendants of some vertex that will overtake that vertex. So do the descendants change? No. Descendants of x and y change, but no one else, their descendants change. It's just a swap of two adjacent elements. Okay. Will overtaking change? No. I mean, overtaking doesn't change. If you're going to be overtaken by x before, you'll still be overtaken by x. And it's still a descendant. Unless it was y, the y is the only one for which it changed. Okay, so we only have to think about x and y and how their potentials are changing. Okay. So let's look at x. X is pretty simple. X went down. So we care about now the descendants of x. Those are what used to be the descendants of y. Okay, so what are the descendants of y that will overtake x? That is phi of t x y. That's the definition here. The descendants of y that will overtake x. We had that written down. So that is its new potential, except there's a -1 because y used to be a descendant that would overtake x, but it just overtook x. Not going to happen again. Not going to happen again. I'm assuming here affine motion, I suppose. Could really happen a constant number of times, but let's keep it simple. Okay, that was easy. Next one's a little harder. The other one is y. What is the new potential of y? Y has new descendants now. It used to just have this many descendants. Still has those descendants. It now has x, which doesn't matter if we assume they'll never be overtaken again. And now it has this whole subtree of z. Okay, so we have whatever it used to have, which is phi of ty. That's all its old descendants. And now we have this new thing, phi of t y z. If you plug that into here, that's the number of descendants of z that will overtake y. That's the new thing that we add on. Okay, so this is an increase. This was a decrease, and this is an increase. We hope that they're about the same. In fact, they will be basically equal. So first claim is this is at most this other thing, phi of ty, phi of t x z. Okay, so I'm just replacing this y with an x. Why is this true? Because if you're going to, this is overtaking y. If you're going to overtake y at this time, you would overtake x at this time. Because x and y are equal right now. I'm pretty sure this is actually equal. I don't know why I wrote in my notes less than or equal to. Less than or equal to is all I need. But I think at this moment in time, when they're actually equal to each other, doesn't matter whether you have x and y here. You will overtake one if and only if you overtake the other at this moment. No, I see. Right. Actually, we care about, this is about future time. In future time, we know that y is always going to be less than x because it's moving up. In future time, if you overtake y, you'll certainly overtake x. Because, no, the other way around. If you overtake x, meaning you go below x, one of these ways. If I go, overtaking is going up in the tree, but it's actually getting smaller in value. If you get smaller than y, you rise above y, that means you will have already risen above x. You will already be a value smaller than x. So hopefully that is the way that is less than or equal to. So that's what we need. Okay? Good. Now I understand. We're assuming affine. Yeah. Sorry. Forgot to mention that. I think this works for pseudo-algebraic, but this proof does not. Assuming that x and y only switch places once. Okay, then we have this simple equation, which is phi of tx equals phi of txy plus phi of txz, where you just sum over the two children. So this is phi of txz. So I need more space, I guess. So phi of txz, that is phi of tx minus phi of txy. So we have, same left-hand side, is less than or equal to phi of ty plus, this is what we had before, t of xz. But now that is the same as phi of tx minus the other child. So, y. Okay, that was just that equation. Now, do things simplify? I hope so. Phi of ty. These two things. Okay. Not so pretty. What we care about is the sum of these things. We care about the sum, the overall potential. So we want phi of t plus is phi of t plus something. How it changes is, well, how does phi of t prime x change? Well, it went down a lot. It went all the way down to phi of t x y. Okay, well, actually, we just add these together. Add them up. This is messy, sorry. Let's look at this sum, phi of t plus x and y. So we get this thing, phi of txy minus 1. And then we get this thing, so phi of ty plus phi of tx minus phi of txy. It's an elaborate way of saying this cancels with this. So we are left with the old value, phi of tx plus phi of ty, minus 1. So that means this is less than or equal to. This means phi of t plus is less than or equal to phi of t minus 1. In other words, every time an event happens, the potential goes down by at least 1. This is basically confirming this intuition, but roughly. Okay, but our definition was this. Number of descendants of x overtake x in the future. How big could this thing be? It is at most the sum over all nodes of the number of descendants of that node. So it's by definition at most n log n. If we look at phi of 0, it's order n log n. We're using a balanced heap here. And so if we're order n log n, initially in every event that happens, we go down by 1, and we never negative. That thing is always non-negative. Then the number of events is at most order n log n. Cool? Okay. Only have one more page of notes to cover in 0 minutes. 15 seconds. Let me quickly tell you about what's on this page, and you can read it at home. It's a little survey of lots of different kinetic data structures, in particular for more than one dimension. So there's a lot of work on 2D convex hull. You have moving points in 2 dimensions. You want to maintain the convex hull. The number of events, the best we know how to achieve is order n to the 2 plus epsilon, a little bit bigger than n squared. And there's a lower bound that it can change n squared times. So it's almost optimal. Unknown how to do that in 3D. A problem that we solved in the open problem session in this class 2 years ago is smallest enclosing disk. So you have points moving in the plane, and you want to maintain what is the smallest enclosing disk of those points. The number of events we got was n to the 3 plus epsilon, which is a little bit painful. Best lower bound is n squared. So still a gap there. That's closely related to another open problem, which is you want to maintain something called a Delaunay triangulation. If you know what that is, great. If not, it's a big open problem. How many times can the Delaunay triangulation change if you have just points moving along straight lines? Best upper bound is n cubed, best lower bound is n squared. So similar linear gap. If you just want to maintain some triangulation on your points, you can do better. Best upper bound is n to the 2.33333. Best lower bound is n squared. So smaller gap, and just cube root of n gap. Collision detection is probably the most obvious application here. You have a video game, things are moving with known velocities. You update those velocities, like you have bullets and people running around, whatever you want to know when they bounce into each other, walls which are stationary. When does that happen? There's pretty good algorithms for kinetic collision detection, although it's very unclear what efficient means. because you want to optimize for the case when not many collisions happen. And these algorithms do, in a certain sense, they're optimal, but it's much harder to state what that sense is. Minimum spanning tree is another one I have. This is tough. Easy thing to do is do kinetic predecessor on the entire sorted order of the edge lengths. And then you just run a thing that processes the edges in order. So that gets a quadratic number of events. It's unknown whether you can do any better for minimum spanning tree. So that was your quick survey of kinetic, and that ends geometry. The end.